Hello. Now that we're done with chapter one, vector analysis, we can now jump into uh, the basic principles of electricity, and we will attempt to describe them using the discussed tool, vector analysis from chapter one. So under chapter two, electrostatics, this is also divided into different subtopics. And the first topic we'll be talking about is the Coulombs Law. Coulombs Law and electric field intensity. So this is now the start of the actual electromagnetism. And remember the uh, tool that we discussed in chapter 1, vector calculus, vector analysis into three different coordinate systems. We will all be using them here in chapter 2. So the first one, the fundamental laws of electrostatic. The Coulombs Law. So Coulombs Law. There are basically two laws under this one. The first law is very simple. First law of electrostatic. The like charges repel each other. And unlike charges attract each other. Charges was defined in your circuits 1, actually, your circuits 1. We already know what are charges. Charges, these are electrons, and the unit for charge is Coulomb. This is another way of quantifying the electrons inside a matter. So those are charges. So if we try to draw, we have a sphere of charge plus. Then we have another plus here. So if these are spheres of charge, then what happens? There's a direction. What happened to them? Because they have the same sign. They are like charges. So there will be a force experience between the two. And that force will be a repulsive force, and the direction will be, this should be, they are going to repel each other. So there's lines here. That will force them to repel each other. And so on. So the direction of the force will be in that direction, outward. Because they are repelling each other. Because they have like charges. They are both positive. Then, also, it can also be this is also true if they are both negative. But if they have unlike charges, what happens to them? They attract each other. Or before that, if we have a positive charge, the direction of the line should be outward. So these first two here, cannot do that one. because it will be, for a negative charge, the direction of the line will be the opposite direction. So if we try to redraw this again, this is negative, and if this is negative, then instead of going into that direction, they'll be in that direction. So the opposite, because it's negative. Then for positive and negative unlike charges, they should attract each other, plus and minus, and the movement should be, because for positive it should be outward, for negative should be inward, so the direction will be in that direction. The lines should be in that direction, and so on. So, unlike charges attract each other, like charges repel each other. That's the first law. The first law determines the direction of the charges when they are attracted or repelled. So from that, we can determine their direction. And the other one is, if we want to determine the magnitude of the force experienced by the charges, and that will be second law. And by the way, the second law was formulated, or Coulombs Law was formulated by a colonel, a French army engineer named Colonel Charles Coulomb. And he said, through experiment, when two charges are placed near or a certain distance between each other. So we have a charge Q here and another charge, this is Q1, then another charge Q2. It can be positive, it can be negative. The direction depends on that sign. If it's both positive, then the direction will be repel each other. If it's both they are unlike charges, positive and negative, then the direction will they attract each other. But the magnitude of that force, according to the Coulombs Law, is somewhat similar with the Newton's gravitational law. It's proportional to the product of the charges and inversely proportional to if the distance between them from the center, the other center is a distance, let's just say r. We use r in chapter 1, so we just use r for the distance, or the vector. Let's just put up absolute value here to indicate that this is a scalar quantity. So then it should be inversely proportional to the square of that distance between them. So to remove the proportionality symbol, there's a proportionality constant K, and this will be Q1 times Q2 all over that distance square. Then if you want to include the direction, the vector F now will be just equal to Q1, Q2, absolute value of that one. Then the direction will be in the direction of the distance, the displacement, or here, and that depends on the design of the charges that we will be including Q1 and Q2. Now, K here, this proportionality constant, they call it, it's just a constant, and it depends on whether the medium between the charges, if it's air or not air, it can be ceramic or anything that can be put between the charges. K here will be equal to K will be equal to 1 over 4 pi epsilon naught, where epsilon naught, this is called the permittivity of free space. Permittivity of free space. And this is constant, and the value for this one is epsilon naught is equal to 8.854 times 10 to the negative 12, or this is around 1 over 36 pi times 10 to the negative 9. And the unit for this is not unitless. There is a unit for epsilon naught, because if you look at the equation, our equation here, the unit for force is Newton. Then the unit for Q is in Coulomb. So we put here Q, this is in Coulomb. Coulomb. Or C, that's C. The unit for Q is C, Coulomb. Then the unit for the force, the magnitude of the force is in Newton. Newton, or simply N. And the unit for the displacement, the distance, is in meters. M. So if you look at this one, the unit for K should not be, or epsilon naught, in this manner, or K, epsilon naught, is not unitless, because if we multiply Coulomb times Q times Q, it's Coulomb squared divided by meter. So what happens? So Coulomb squared per meter. We need to come up with a unit in terms of Newton for the force, because force is in Newton. So there should be a unit for that one, the K value, so that the unit that will be coming will be in terms of Newton. So we need to, what do we multiply with Coulomb squared per meter to make it a Newton unit? So we need to multiply that with, this should be squared here. This should be Coulomb squared per meter squared. So we need to multiply this one with a meter squared, so that the meter will cancel out, and also a Coulomb squared, so that the Coulomb will cancel out. Then we multiply it with a Newton. So if we multiply them, the only unit that will be coming will be a Newton, because the formula is the formula for the force, and the unit for force is Newton. So this should be the unit of K, so that we have a unit of Newton for the force. But there's a simpler unit for this one, because we don't want our unit to be look like this. So we need to multiply. There's another unit, we call it the farad unit, 1 farad, the unit for capacitance, and this is equivalent to Coulomb squared per 1 Coulomb squared per Newton meter. That's 1 farad. So if we use that, the unit for, so if we go back to this 1 meter squared per Coulomb squared times Newton, that's actually the K. But if we go back for epsilon naught, we need to know the unit for epsilon naught. So we should inverse that, because it's 1 over 4 pi epsilon naught. It will be Coulomb squared per meter squared meter squared Newton. And that one, Coulomb squared per meter squared Newton. So the 1 meter, the 1 meter here will remain, while the other one will be inside that farad, and that's equivalent to 1 farad. So therefore, the unit for epsilon naught, the permittivity of free space, will be in terms of farad per meter. So this will be in farad per meter. So the unit here should be in farad per meter. So instead of using that one, Coulomb squared per Newton meter, or Newton meter squared, we just use farad per meter, because later on, the application for electrostatic, we will relate this one with the application. And the main application for electrostatic in electrical engineering will be a capacitor. And we know that the unit for the capacitance of capacitor should be in terms of farad. So to relate them, the value for the unit for the permittivity should be, we use this farad per meter instead of that Coulomb squared or Newton meter. Then, but in general, this K here, this 8.1/4 pi epsilon naught, this is for free space. This is the value of K in free space. So if we try to solve that constant for free space, the value of K will be equal to around 9 times 10 to the 9. 9 times 10 to the 9. Then, if it's not in free space, for in general, not in free space, the value for K will be a different value. K will be equal to 1/4 pi epsilon naught times another permittivity, and this epsilon, relative permittivity epsilon r. This is the permittivity epsilon r, because it's not space. Permittivity, relative permittivity, relative permittivity of, or they also call this one the dielectric constant. Dielectric constant. That is the permittivity of the dielectric, or the medium, if it's not in free space. So the general formula for the force in vector form will be Q1 times Q2 all over 4 pi epsilon naught times epsilon r. Epsilon naught times epsilon r. Then you multiply it with the distance, then the direction. Now this direction and this magnitude, so if you look at that, so if we write this over this one, it's familiar for us when we are determining, remember the unit vector in chapter 1, unit vector. If you want to determine the unit vector of a certain vector r, AR is equal to that vector divided by its magnitude. That vector divided by its magnitude. So if you look at this one, so if I substitute the unit vector here, our formula will become F Q1 Q2 over 4 pi epsilon naught epsilon r. Then you multiply it with this is squared, r squared. So if we multiply it, if I substitute r over absolute value r, so if we have r squared here. Then I multiply it with AR, which is R over R. Then what happens is, remember, R here will be a vector. It's the vector. It's a position vector, or the directed vector. Later on, directed vector Q1, Q2 all over 4 pi epsilon naught epsilon R, then absolute R times R. This will be absolute R cube. Then you multiply it with the vector R. And this will be the general formula for the Coulombs law that we will be using. The vector R here can be determined by determining the position vectors of Q1 and Q2. Q1 and Q2 will be just the point along our coordinate, the point. Then, if you want to determine vector R, that is the directed vector or displacement vector from Q1 to Q2 or Q2 to Q3, or depends on the sign. Remember, it depends on the sign of Q1 and Q2, or if it's positive or negative, like charges and like charges. So let's take an example to illustrate this. Example. Find the force on charge Q1 with charge positive 10 microcoulomb. Micro means times 10 to the negative 6 coulomb, due to Q2, another charge with the sign of negative, with the charge of negative 100 microcoulomb. Q1 is located at 0.012 in rectangular coordinate system, and Q2 is also can be located at 2, 0, 0. So first we need to draw this one. So let's draw a three-dimensional. So this is z-axis. This is the z-axis, and this will be our y-axis, and this dashed line will be our x-axis. So now we want to locate the first one, Q1 versus Q1. Q1 is at 0, 1, 2. So 0 for x and 1 for the y-axis, and we count 1, 2 for the z. So the Q1 will be somewhere here. So this will be our positive Q1, which is equal to 10 microcoulomb. So this is Q1. This point here is Q1. And then the other charge is located at 2, 0, 0. So positive 2 for x, so 1, 2. And the rest is 0. So this will be our Q2. And it should be equal to negative 100 microcoulomb. So what will be the force experienced on charge Q1? That's the question. What will be the force in charge Q1? And what will be the direction? Because they are unlike charges. So what happens if they are unlike charges? What will be the direction of F? Let's call it F1. So the F1, because it's on Q1. So let's call it F1. So this will be our directed vector, dr, and because it's 2 and 1. So what will be the direction of the force, or R? What will be our R? We can choose R to be in that direction. So let's call it R21. So from 2 to 1, vector 2, point 2 to point 1. Then we are the position vectors, the small r's. Remember the small r's. We have here the position vector here. We can call this one R2 because that's point 2, and the other one here, we can call this one R1. So if you want to solve for vector R21, R21 now is simply equal to the difference between that position vectors. It's just equal to R2 minus R1. Or it should be the other way around because it's R21 not R12. The end point, the end should be the beginning. So this should be R1 minus R2. R1 minus R2. Where R1 is the position vector of Q1 and the coordinate of Q1 is 0, 1, and 2. While the coordinate of Q2 is 2, 0, 0. So R1 now will be equal to, there's no AX, there's no X component, but there's a Y component, so AY, and with the magnitude of 1. Then plus 2, Z component, AZ. And for R2 to 0, 0, so there's a X component, so 2AX. Then if we subtract them, R1 minus R2, R21 now will be equal to, there's no AX here, so 0AX minus 2AX is negative 2AX. Then AY minus 0, so plus AY, then plus 2AZ. So this will be R21. And from this, we can derive the distance between the two charges. And how do we determine the distance? We just take the magnitude of that vector. So what's the magnitude of a vector? How do we get the magnitude? We use this formula. Take all the components, square them, and then add them. So negative 2 squared plus 1 squared plus 2 squared. So R21 now, the magnitude will be equal to 4 plus 4, 8 plus 1, 9 squared of 9 is 3. 3 units or 3 meters. Then, what else? We can now use the formula, this one, because we know the vector, we know the magnitude. And we assume that this one is in free space because there's no given relative permittivity. So if the problem does not tell that there's a medium between those charges, we always assume that the medium is air. So the value of K here should be equal to 9 times 10 to the 9. So if we solve now for the force F1, because we're solving for the force at Q1, and this will be equal to Q1 times Q2. Q1 is what? Q1 is 10 microcoulomb. So this is 10 times 10 to the negative 6. 10 times 10 to the negative 6. Then we multiply it with the negative. We need to include the negative. 100 microcoulomb times 10 to the negative 6. Now here, I included negative because I assumed that I don't know the direction. I did not apply the first law, R21. I just use arbitrarily R21, so this vector from 2 to 1. But I know, if you know the first law, that the direction of the force should be in that direction because they attract each other, because they are unlike charges. It should be F1. And this is F2. F1. So then, we don't know that, but because we multiply it with negative 100, so the direction should be in that direction. All over 4 pi epsilon naught. Don't use 9 times 10 to the 9. You cannot. You can use it, but because the calculator, using your calculator, there's epsilon naught in your calculator. It's a constant, so you can use it directly. So your calculator here. So if this is your calcu, sheep constant, sheep 7. Then you choose where's the constant epsilon naught. It's I think it's number 32, constant 32. That's epsilon naught, and that's 8.854 something. So you don't need to memorize the value for epsilon naught. You can just simply plug in epsilon naught constant from your calculator. 32, constant 32. So epsilon naught, then because this is in free space, epsilon r, the relative permittivity of free space will be 1. So you multiply it by 1. Then we multiply it with the displacement, the magnitude. The magnitude is 3, and you need to cube that one. So 3 cube. Then multiply it with the vector r21, and that's negative 2ax, because this is a vector, negative 2ax plus ay and plus 2az. Then if you calculate this, this will be 10 exponent negative 6 times negative 100 exponent negative 6, then all over 4, shape pi, and shape constant 32 epsilon naught, then times 3 cube, and this will be that one, equals, so it's negative 4.3328. Negative 0.33287. Then you multiply it with negative 2ax plus ay plus 2az. Then we distribute that, so f1, vector f1 will be equal to, multiply it by negative 2. So negative, negative, so this should be positive 0.6657ax, then minus 0.33287ay, then it's minus 2 times that one, 0.33287, or it should be 6657 times 2. 657 AZ. So this is now the force in vector form. Now, most of the time we don't want that force in vector form. We want to determine the magnitude of that vector. So if you want to determine the magnitude F1, this will be equal to the square root of those components, square root of 0.6657 squared plus 0.33287 squared plus 0.6657 squared. So the magnitude now of force experience at the Q1 will be 0.6657 squared plus 0.33287 squared, then plus 0.6657 squared, square root. This will be around 0.99856, and the unit will be Newton. So this will be the magnitude at Q1. It's the same also, that should also be the magnitude at Q2, F2. The only difference between them is the direction. And if you want to determine the direction or the unit vector of this one, A A AR or AF1, the direction of this AF1 should be equal to the vector 0.6657 AX minus 0.33287 AY minus 0.6657 AZ, and you divide this one with 0.99856. So the direction will be the unit vector AX minus 0.33287 minus 0.333 AY, then it's the same 0.6667. Easy. So this will be the vector or the unit vector or the direction of that vector F1. In fraction, this is 2/3 AX minus 1/3 AY minus 2/3 AZ. So if we go back here, let's zoom in. So where is that point? So we have 2/3, positive 2/3 from here. If this is 1, so it's around here, 2/3. Then we have the other one is 1/3 in the y direction. So in this direction, then we have another 2/3 in the z direction. Sorry, this should be negative because the y component is negative and the z component is also negative. It's positive 2/3, then we have negative 1/3, and we have negative 2/3. Now, to illustrate that, I draw something here in GeoGebra.org. So here, this is our vector. The green one, this is the displacement vector R21, and I plotted the unit vector, this red one here. So this means that the direction of the force should be in the same direction as that. So, but instead of starting at the origin, it would start at point, at this point or at this point. It's the same as long as the direction is in that direction, downwards. So it's toward Q2. So this means that the vector that we get, unit vector that we get, and that's 2/3, negative 1/3, and negative 2/3. And that's the correct direction for the force. And the magnitude that we get was around 0.99856 or around 1 Newton at point F1. So now if we want to determine, what if I want to determine the force F2? So for the force F2, it's the same magnitude, it's also the same as 0.99856. The only difference is the direction. So now from here, instead of using R21, this one R21, it should be the other way around, R12. It should be R1 minus or R2 minus R1, not R1 minus R2. And we can write that one as, you can just put negative on the unit vector because it's the opposite. So here, F1, vector F1 will be equal to the negative of F2. They have the same magnitude, but there's a negative. It means that they have the opposite direction to each other. Now if we have more than two charges that is in the space, to solve for the force experienced by one of them, one of the charges, we can use the principle of superposition. It's applicable superposition. It's like in circuit. What do we mean by superposition? So if we have, for example, more than 3 or 4 vectors, we have positive Q1, negative Q2, positive Q3, and you have still here negative Q4. Now I want to determine the force experienced by Q1. So what we do using superposition is you remove all the other charges except one. So here you can disregard Q3 and Q4 and solve for the force that is contributed by Q2. So it's positive, this is negative. So the direction of the force should be in that force. That's F12. Then you do that again, but this time with Q3. So what will be the force due to Q3? So Q3, they are both positive, so they repel each other. So the direction should be in this direction. This is F31, so from 3 to 1. Then for Q4, positive and negative attracts, so it's also in that direction, and it should be F14. Then to solve for F1, F1 is just equal to the sum of all the forces, F12 plus F14 plus F31. That's the net force that is being experienced at Q1. So that's superposition. You can do that. If you want to Q2, you do it again, but do it one at a time. Then after that, you take the net or the total, you just add all the effects of each charges. It's like in circuit. We remove all the sources, then we just put one source, then we determine the effect of that. Then afterward, do it again with the other sources. Then afterwards, you add them all. But before we do the example in superposition, there are two types of unit system that we use in electromag under SI, Standard Unit International Unit System. We have what we call the MKS system, and we have the CGS system. In MKS system, this means meters, kilo, second, kilometers, meters, and in terms of kilo, where CGS is in terms of centimeters and grams, kilograms and grams, second. So in MKS, our value for K is equal to 9 times 10 to the 9, around 9 times 10 to the 9. Now for CGS, the value of K is just equal to 1. But in MKS, our force is in Newton. Our Q's are in Coulomb, and our distance is in meter. But here in CGS, it's different because it's in CGS system. The unit for force in CGS will be in terms of dyne, and for Q The unit should be in, we call it stat column, stat C. And for R, it should be in centimeter. So why do we need this one? Because in CGS, if you're working with the centimeters, small distances, which usually we do in electrical engineering in terms of centimeters, then it's good to use CGS, and it's also good because K is equal to 1. So the formula will be just equal to F is equal to Q1 times Q2 over D squared. But remember, Q should be in stat column. The distance should be in centimeter, and the result is not in Newton, and it should be in dyne. And what will be the conversion between these two? One coulomb is equivalent to 3 times 10 to the 9 stat coulomb. And 1 Newton is equivalent to 100,000 of dyne. And in meters to centimeter, 100 centimeter is for 1 meter. This is the conversion between the two systems. So when you're solving problems using Coulombs Law, make sure do not combine these two systems. Do not use centimeter while using Q as coulomb. Do not use stat coulomb when using meters. The result is not equal to Newton. So you need to be consistent. So if you use dyne, you use stat coulomb, you use centimeter, the constant should be equal to 1. You don't use 9 times 10 to the 9. This is if we are in free space. Remember, this key here is if we are in free space. This is only true k is equal to 1 if we are in free space. But if it's not in free space, then use our general formula for that. Okay, so for the next video, we will be solving more problems. I will give you more examples. Then after that, we will go to the next topic, the electric field intensity.